সৈকত স্যার আর 2 মিনিট পরে শুরু করে দেওয়া যাবে।
ঠিক আছে। ওই অনির্বাণ স্ক্রিনটা প্রেজেন্ট করবে তো?
না, ওটাও এডিটে করছে, এটা করার।
আচ্ছা, তুই তাহলে বলার পর
হ্যাঁ, we request all the participants to please mute their respective mics.
কারেক্ট ফোন বাজছে।
Thank you.
Someone has his phone unmuted and it's ringing.
সৈকত স্যার, hello, Saikat sir.
Yes, sir.
I think we should start. It's 5.
Yes, we should. Anyway, let's start. Dipankar, then I'm starting.
Yes, sir. Surely.
Good evening, dear friends. It's my pleasure to welcome you all on behalf of Skywatchers Association Kolkata to be a part of this very new venture of Skywatchers Association. I'd just like to start with a quotation from Brian May, a renowned physicist, astrophysicist, a musician, and whatnot. He once said that it is much more fun when you are not an astronomer. At Skywatchers Association Kolkata, we are all sky enthusiasts. We love the sky, so we love sky watching also. And we also love the science that goes with it. What keeps us together? And I believe all of you who have come here today love the sky too. We all love astronomy in any form. Now these times, lockdown, go the look for dark skies to enjoy a nice session of sky watching, it's become difficult. Skywatchers, we came up with a new plan. Why not enrich ourselves while sitting at home? Naturally, we're not being able to leave our homes. We have to stay indoors with a lot of restrictions. So this was the plan, that why don't we start enriching ourselves while being at home. Interacted among ourselves, that was okay. But to enrich ourselves, we really needed people who could show us the way. There are some people here, there are some people always here who are very kind, very generous, just so generous that they didn't think a second time to share their vast knowledge with us. Now, this knowledge sharing is an integral part of Skywatchers Association. Whatever little we know, we enjoy sharing it with anyone who just wants to know. Today, we will be listening to a renowned astrophysicist. The person whom I'm going to hand over the mic to next, he'll give you a brief introduction of him. Now, this webinar is a result of that pursuit. We wanted to enrich ourselves, as well as, when we could do so, share it with what we could get with everyone else. Today's speaker is Dr. Biman Nath, who is a professor at the Ares Institute, and he will be speaking on our neighborhood stars. Now, the love for the cosmos has brought us here today. Our cosmic neighborhood, the universe, is basically our backyard, our mahalla. Now, we need to know our mahalla very well. We need to know our backyard very well. We believe that astronomy is, it cannot be. Telescopes are simply the instruments with which we can have a peek at the universe, some objects at the most, but that's not all. The reality is the truth behind what we see. What are they? Why are they there? How are they there? How are they related to us? If these questions remain unanswered, then those dots of life, those dots of lights will ever remain just dots of lights and nothing else. We need to know about them. Stephen Hawking once said, look up at the stars and not down at your feet of what you see and wonder about what makes the universe. Be curious. I sincerely believe that we all will enjoy this lecture and take back with us at least something that we can share with the others. But there's one more point. We will not forget this. That is, we at Skywatchers Association have a very strong social responsibility. From that, I'd like to say, please be safe in these times. Maintain proper social and physical distancing. Wash your hands with soap for at least 20 seconds. Sanitize your hands and do wear a mask whenever outdoors. Please. The second most important thing, please do not ostracize COVID positive patients. They need our help and support. They are earthlings like us. Do look up at the sky. With these words, I'm handing over the mic to Dipankar De, who also is the General Secretary of Skywatchers Association, to take you to the rest of the program. He will be the coordinator today. Come, let's start the journey together. Dipankar.
Thank you, Shoykot sir. Yes, sir. I think I am audible.
Yes.
Hello.
Yeah, we can hear you.
Thank you, sir, for such a nice introduction. You have said probably all the things what I have planned to say. So one thing just I want to mention that today is Saturday, and actually every Saturday we used to meet at Skywatchers Association from 5 p.m. to 8 every week. We know that we have to close our station due to this, and we were thinking indeed. So how can we reach to the people? That is the main aim or for us in every aspect. How can we outreach programs for everyone? And from that point of view, we came with the idea that let's say we like some topics and covering some
Dipankar, if you can
astronomy.
switch
Then
off your
we have some
video, speak and just speak.
Okay.
Switch off your camera, just speak.
Okay, sir.
Great.
Now, is it? Hello.
Yes, switch off your camera and just speak.
Okay. Is it fine? Am I audible?
Yes, now carry on.
না দেখা যাচ্ছে না তো
Okay.
দেখার দরকার নেই।
Oh, no, sir. ভিডিওটা অফ করা আছে। সাউন্ড শোনা যাচ্ছে তো?
Carry on. হ্যাঁ, carry on.
Okay. Okay. So then, when we first thought about this type of webinar, and we mailed a few persons who can really teach us about this topic, and we are very thankful to Professor Biman Nath of Honor Institute that he readily agreed to give this webinar, and with such an interesting topic that our neighborhood stars. So into further ado or something like that, I now request directly Professor Nath to say a few words and deliver his talk. And I forgot to mention that please, it's a request to everyone to mute their audio and pause their video also. And if you have any question in the lecture session, please type it in the respective chat boxes. Do not unmute yourself in between the lecture and start asking your question. There will be a question answer interactive session at the end of the talk, and you will get to unmute yourself and ask your questions then. But for now, as the session ended by Professor Nath, please mute your and both, and do not present your screen. Otherwise, there will be problem in viewing the presentation and also the lecture. Professor Nath, please do click pin to screen to the presentation of Professor Nath so that you can clearly view the presentation without having any disturbance. So it's time to hand over the session to Professor. And please, sir, if you.
Thank you. Thank you, Dipankar Babu, and Mr. Shekhar also, and all the members of the Sky Watchers Association for having me in this platform. It would have been more exciting to meet you all in person at your the place where you watch the sky. But I suppose in this situation, in these circumstances, it's not going to be possible for some time to come. But technology allows us to meet online like this. So thank you again. So let me ask you, am I audible? I mean, if there is any problem, just let me know so that I can repeat what I have said.
Sir, you're coming in very clear and crisp. You are very clear and crisp.
Right. So let me now then share the screen, and then I'll go over to right. So I wanted to talk about the stars that are located close to us, and especially because it's a Sky Watchers Association. Most of you, and if not all of you, have been looking at the sky, and you know most of the stars that are visible to us every night. And I wanted to talk about some of the interesting things about the stars that we see almost every night, like Sirius, like Altair, and stars like that. And most of the stars that I'll explain are located very close to us. And I'll also tell you what I mean by very close to us. And the reason I wanted to talk about these stars is that there are interesting things to talk about. What happens in our neighborhood, what has happened in our neighborhood, especially when you look at the headline news that makes in astronomy. Most of the times you hear about black holes and the beginning of the universe, or what's happening at the edge of the universe, gigantic explosions and exotic objects. It's like, you know, when you want to plan a travel, we always think of distant places, and we often tend to ignore some of the interesting things that lie very close to us in neighboring places. And what I would like to say that, you know, there are interesting objects in our neighborhood. There are enormous star clusters with very young and bright stars. There are clouds of gas which are nothing but ashes from stars that have exploded. There is also an exotic object. There are pulsars, and which was probably created at in the aftermath of a stellar explosion. And it's also likely there are other signs of stellar explosions nearby, and I'll tell you some interesting things about them. Now, often we don't think about these objects. What's the nearby stars is that we think it's a very mediocre place, and the stars and objects that are located in this region are also going to be mediocre. After all, Sun is an average star. In terms of mass, it's not very massive, or nor is it a very low mass star. And since temperature depends on the mass of a star, its color, the yellow color, is also somewhere in the middle of the spectrum, from blue color of hot stars and red color of very cool stars, low mass stars. It's somewhere in the middle. It's also a very middle-aged star. The Sun is likely to take about 10 billion years to run out of its thermonuclear fuel, and it has already been shining for about 4.5 billion years, and is going to remain like this for about 5 billion years to come. So it's somewhere in the middle. You know, it's a middle-aged star. And but there are interesting objects in our neighborhood. So let's begin the journey from some the places that we know, that we are more familiar with. So this is the solar system. I hope you can see my screen. So I'm going to try to zoom out of the solar system because this is a familiar territory. And on the left-hand side, you can see the orbits of the inner planets, that of Mercury, Venus, and Earth, and Mars. And you can see that the yellow orbit is that of the Jupiter. And so this is a box size. So we are basically looking at the Sun from a distance of about 10 to the 12 meters, 1 billion kilometers. Okay, so Jupiter's orbit, which is about so it is just about cross Jupiter's orbit here. If we go out even further, say 10 times more distance, 10 billion kilometers away, we would see all the orbits. Now, this is a picture that I have taken. Is a picture outdates. It's somewhat outdated. It shows the orbit of Pluto, which is not considered a planet anymore. But ignore that. And at this point, I think we should move to. I would like to move to a different unit of distance. Otherwise, we'll be lost in millions and billions. And so, a more helpful unit of distance is the light travel time. So the sunlight takes about 8.5 minutes to reach the Earth. That's the light distance. Neptune is about 4 light hours away from the Sun. And so in this way, we will be able to keep up with the larger and larger distances that we'll encounter. So I'm going to zoom out even further from the solar system. Now from 100 billion kilometers, where you can see the solar system in the perspective of its neighborhood. And if we keep going out, say at the bottom right corner, it's a distance of about light year. So we're looking at the solar system and the sun from a distance of about light year. And it looks like sun is the brightest star at that distance. Because to reach the nearest star, we'll need a few light years. If we go out further, at about 10 light years, then we'll see other bright stars coming into view. And then if we go out to say 1,000 light years, we'll see that our sun, our solar system, is lost in the crowd of many other stars, and there's a lot of gas clouds, the dusty regions. The black regions are dusty because that dust absorbs light from the background distant stars. And then about 10,000 light years, we would see that, again, sun is a mediocre star. And it's an average star. There's nothing remarkable about it. There's nothing remarkable about this, the location that we are in our Milky Way. So if we zoom out to about, say, 1 million light years, we would get to see our galaxy. So that's on the the right-hand side. You'll see a galaxy. It's a spiral galaxy. Milky Way is a spiral galaxy. We cannot go out of the Milky Way, of course, with present technology, but this is what it would have looked like if we could go out of the galaxy. And on near Milky Way, there is Andromeda galaxy, because at that distance we will also be able to see Andromeda galaxy. Anyway, so this Milky Way galaxy is a spiral galaxy. It has a lot of spiral arms, and it is about 30,000 light years in radius, and it's very thin. And let's look at the region. Let's look at Milky Way. This is Milky Way. It's a schematic diagram, of course, but it's drawn out of the knowledge that has been gained from different types of observations. And so this is where we are, the sun and the solar system. We are in one of the arms. It's called the Orion arm, and I'll tell you why it's called Orion arm. And as you can see, we are very far from the center. It's about 25,000 light years away from the center of the galaxy. And thank heavens for that, basically. Because if we had been close to the exotic objects that are there in the center of the galaxy, for example, there's a black hole there, we would have been bombarded with harmful and powerful radiations, and which could have been dangerous for evolution of life on Earth. And this is something that I would like to keep coming back to later on also. So what do I mean by neighborhood? I mean, I have to give I have to be more specific about how large a region I mean. So what I have in mind is a region of about 500 light years across in diameter. And the reason is that this is a sort of a map of the stars which are visible to us. When we look up the sky, the stars that we see are all lying within, they lie within at the most 1,000 light years from us, because there's a lot of dust in the Milky Way which absorbs the light from more distant stars. So we cannot see the stars which like very close to, say, galactic center, or more than 1,000 light years away. So these are the stars we are familiar with. These are the stars we see every night. And you, the sky watchers who love the sky, as Mr. Bhadra has mentioned earlier, you have seen all this. Yep. Yes. Yes. Right. I cannot seem to. Let me see. I have to go out of this. Okay. All right. Okay. Right. Okay. Thank you. Okay. So now I want to let's focus on a region very close to the sun, so within about 50 light years. Right. Now I've taken this figure from. This is a schematic diagram. I've taken this from an article by Priscilla Frisch, which came out in American Scientist. It's easily available in the internet. It's a very, very interesting article. It came out in 2000. So in the middle of the picture, you will see the sun. Don't worry about the arrows right now, the motion and things like that. Just I want to. So this is the region about 50 light years away. And you can see the Alpha Centauri, which is about 4.5 light years away from us. This is the nearest star. You can also see Sirius on the right-hand side, which is the brightest star in our sky. You also see Procyon. Sirius is about 9 light years, not very far, right? And Procyon is also close by. I mean, it's a coincidence that these two stars, I'm sure you know that they appear very close to each other in the sky, east of the Orion constellation. But they also, I mean, they happen to be close to one another in reality. On the other side, on the left-hand side, you also see Altair. That's a bright star. I mean, that's a okay. That's I'm sure this is the sky you are familiar with. So, on the left-hand side, you see the Summer Triangle, right? The Vega, Deneb, and Altair. That's the Summer Triangle. So that's the Altair. The Altair is very close to us. And on the right-hand side, I'm showing the Orion constellation and Sirius and Procyon. So these are the stars very close to us. But what's even more interesting is what lies between the stars. You can see the whitish, grayish wisps of cloud, and that's what I want to focus on now. You can see that the sun is bathed, sun is immersed in a bath of hot gas that is coming from somewhere. And and the dark regions are very low density, and just around the sun there is a gas of certain density. I'll come to the details of how dense these clouds are. Now, if I look at this region from a bigger perspective, this is from a perspective of 500 light years across. Now, so this is where the sun, and this is where the sun is, and you can see the yellow parts are slightly high density relatively. The blue parts are very low density, right? And the whole region is called the local bubble because it's a bubble of very hot and very tenuous gas surrounded by this yellow, which is slightly dense region. So it's as if a cavity has been carved out of this region in the galaxy. We'll talk about what processes could have done that later on. But let's, for the time being, let's focus on the sun, and you can see that sun is immersed in this yellow, slightly hot gas, dense gas, and it's called the local fluff or local cloud, which is inside this local bubble. So this gives you an idea of the total length scale, the size of the region. This is 500 light years across. We'll talk about certain the interesting objects in this region. Now, coming to the density, the typical density of air on Earth is about 10 to the 19 molecules per cc, or 10 to the 13 molecules per cubic meter. Now, we know this because this is from high school, physics or chemistry. We know that a mole of gas under standard pressure and temperature contains Avogadro's number of molecules. So this is how we know. Compare this, in contrast, the typical density of gas in the Milky Way is 1. This 1 atom per cc. I mean, 1 cubic centimeter has about 1 atom. This is very, very low density. I mean, it's emptier than even the best vacuum that you can produce in the laboratories on Earth. And compare this to the typical density of gas in the local bubble. The blue region is even 100 or even 1,000 times less dense than even the average density of gas in the Milky Way. As you can see, I've written that, in the case of Earth, the air and atmosphere, I've written molecules because that's we have molecules. When you go to Milky Way, the gas, largely there are molecules, but most of the times you see only atoms. You don't see molecules, are very rare. And in this local bubble, I've written particles because you don't even get to see atoms because it's very hot and it's all ionized. So electrons have been separated from so they're particles. Let's go back to this 50 light years region again. And as you can see, the sun is in the middle. You can see that the wisps of cloud, gas, that is coming from a nearby association, which is shown in orange cloud and the blue, association of stars, the cluster of stars, so the Scorpius and Taurus association, which is very close to the Aquila Rift giant molecular cloud. Now, okay, let me explain some of the terms that I've used here: association of stars, molecular clouds. But before that, I would like to mention that the sun is not at rest in the local bubble. Now, orbital speed, the yellow arrow shows the orbital speed of the direction of the movement of the sun. The sun around the center of the Milky Way is about 220 kilometers per second. And that's a very large speed, a high speed. In a second, we travel 220 kilometers roughly. But most of the stuff in the local bubble is also moving. So the relative speed of the sun with respect to the local bubble is of the order of 20 kilometers per second. That's relative speed. Now, if you can do a back of the envelope estimate, so what is the time that the sun is going to take to cross this whole region of the local bubble? So it's 500 light years divided by the speed. It will give you a time of about, say, 7.5, 8 million years, say 10 million years. So the sun has been, in this local bubble region for about 10 million years. And as you know, this has been, this time frame of about a few million years has been important for evolution of life on Earth. And this region, this dense region around the local bubble, the dense gas, has been very beneficial to us on Earth. It has protected us from the harmful radiation that comes from other directions, other places in the Milky Way. So that's an interesting connection, you know. Our situation, our location in the Milky Way is relevant for what happened and what has happened on Earth. So now, as I said, the gas that is coming towards the sun is coming from an association of stars, and this is another view again taken from the same article. And as you can see, that we are in the Orion arm, and there's a Scorpius and Taurus association. Now, you know the sky, so this is Scorpion. You would be able to recognize on the left-hand side the Scorpion constellation. There's Antares, and on the right-hand side there's Centaurus. And basically, in this direction, there is a young cluster of stars, and that is located very close to Aquila Rift molecular clouds. Now, I want to make some connections with, and to understand the connections between molecular clouds, young star clusters, and why should they be blowing gas, we have to understand the processes of how a star is born. Now, as you know, stars are basically spherical hot balls of gas which is hot enough in the center, in its core, to have thermonuclear reactions, fusion reactions, which can supply the energy which we see as in the form of light. And it requires the fusion reaction. For example, the sun, I'm showing on the right-hand side. In the sun, 4 hydrogen atoms, they combine to form 1 helium nucleus. And in the process, some mass is lost. It's not lost. The mass is basically converted into energy according to E is equal to mc squared. And that's how, and that energy comes to us in the form of light, and this is how stars shine. But it has to have this enormous amount of temperature. It's about 10 million degrees to be able to have this fusion reactions. And how do you create such enormous temperature? Because of pressure, right? As you know from high school physics, if you increase the pressure on a gas, the temperature will rise. And pressure is easy to achieve when you have a large amount of mass because of its gravity. So gravity can pull things inward, create a pressure, and increase the temperature in the core. And that's how you can ignite start the fusion reactions. Now, why should a cloud of gas, for example, in the interstellar region, suddenly start collapsing under its gravity? Usually there's a balance between gravity and the pressure from its temperature of a gas. That balance has to be taken away somehow. And that is done, that happens when you have molecules. And the molecules can cool a gas in interstellar clouds, and that can suddenly, so here is, okay. And that can start a cloud to collapse on its own under its gravity and create such a situation for fusion reaction. So, and there are such clouds in our galaxy which has molecules. There are very dense and very cool, very cold gas. It's about a few tens of Kelvin. Right? And we cannot see these objects because they don't radiate light invisible, right? So with naked eye, we cannot view these objects. For example, I'm showing Orion constellation. This is the familiar Orion constellation. Actually, it's a part of a huge, very large molecular cloud, which you can see if you use infrared light. So this is the region, of the same region in the sky as it appears in infrared. It's a very cool region, so it emits light, but light in the infrared. Right? So, and so these are the places where stars are born. And as you can see in Orion's sword, where I'm sure you have seen with your telescopes the star clusters. So in these molecular clouds, what happens? So sometimes there are some certain disturbances. So it's a schematic diagram of what happens to gas clouds of, cool clouds of gas and dust. If there are some disturbances which can compress these clouds, and then this cloud can fragment, and each fragment would, produce cloudlets and would form stars. So basically what you have is the molecular clouds, certain regions of the molecular clouds forming clusters of, so you have not just one star, but a cluster of stars. And this is a very recent image taken by Hubble Space Telescope of cluster of stars called Westerlund 2 on the right-hand side. And there are, these are young stars, and some of them are very, very massive stars. And an interesting thing about massive stars is that they are very, very bright. They radiate energy at a prodigious rate. And so they run out of their nuclear fuel also very, very quickly. For example, our sun, I mentioned that it would take about 10 billion years to run out of its thermonuclear fuel. If the sun had been 10 times more massive, then it would have been in the, not billions of years, but millions of years, it would have run out of its fuel. So these bright young stars, the massive stars, they are very bright, and which means there's a huge amount of radiation coming out of these stars, and sometimes this radiation can push gas at very high speed. So there is what we call the stellar wind coming out of these very massive stars. Now, stellar wind is not very uncommon. Our sun also has solar wind, which creates, for example, auroras on Earth, and sometimes causes grid failures, power grid failures. But the young stars, the massive stars in such clusters have very high speed of gas, an enormous amount of gas coming out of them. And this is the gas that is coming out of this young star cluster in Scorpius Centaurus association. And this gas is blowing towards us and causing the local cloud. And that's very close to the Aquila rift. As you can see, it's also shown in the arrow sign. An Aquila rift is a giant molecular cloud. I'll show this, and some of you may have seen the Milky Way galaxy in the sky. I mean, these days it's getting very, very difficult to see Milky Way in the sky. But if you have seen, you notice that there's a dark region which is caused by gas clouds and dusty gas clouds, and just near Altair, in the middle of the figure, you will see the Great Rift, and that's where the Aquila, there's another view here. So Altair is on the top left corner, and so on the right hand side, on the middle of this figure, this is a dark region, there's a rift, and that's where the Aquila molecular cloud is, and it's very close to the Scorpius Centaurus association. How am I doing on time? So this is already 40 minutes. Okay. Okay. So what happens when stars run out of their fuel? When a star like the sun runs out of its thermonuclear fuel, it's going to start burning hydrogen outside its core. And there are other reasons that I cannot get into here right now, why this star like sun is going to expand and cool and become red. So the sun will become what we call a red giant star. This is the artist's conception of what the sun would look like from Earth when it becomes red giant. It would eat up the orbits of Mercury, definitely, and maybe even Venus. And so that's going to happen 5 billion years from now. And there are examples of these red giants in our neighborhood, for example. So, you know, Aldebaran, this is the head of the Taurus constellation near Orion. Now, Aldebaran is a star which is about 1.5 times that of the sun, and it's not very far from us. It's I think it's about 65 million light years from us, and it's about am I right? I mean, did I say it correctly? Yeah, 65 light years, and it's about 45 times the size of the sun. So it's a red giant. Another example is Arcturus in Bootis. This is about 34 light years away from us. Now it has not really become as gigantic as Aldebaran, so it's not cooled as much, and it's not a red giant; it's an orange giant. So there are examples from our neighborhood of this stage of the stellar evolution. This is Arcturus. Now there are red stars in our neighborhood. This is Antares. This is the head of the Scorpion. You know, this is a red star. It's not a red giant really. It's a very, very massive star. It's about it's about 15 times the mass of the sun. And now it's not really run out of its nuclear fuel. It's burning. It's hot enough to burn. Get to the next stage of nuclear burning. It's burning its helium right now. It's not really in our neighborhood. It's about 600 light years away, but I just thought I would show an example that all red stars are not red giant stars. And at this red giant phase, what happens to the outer periphery is that the gravity becomes very weak. So the star basically sheds its outer atmosphere, and these are some spectacular pictures of a star at this stage. We call them planetary nebula, but it's nothing to do with planets, but it's just the name that was given a long time ago, and the name has stuck. And these are spectacular pictures. Some of the colors are spectacular. The oxygen, the green color comes from, for example, oxygen ions, W-ionized oxygen. So this is a schematic diagram of evolution of stars that I've been talking about. So from clouds, if it is a small low mass star, it becomes red giant. Then so this is the upper arm that I'm showing, the planetary nebula, and the core of the star becomes a white dwarf star. White dwarf is a star. It's not burning any. There's no fusion reaction going on. It's hot and it's just radiating energy just like any hot object would, and it just slowly cool down. And interestingly, the first white dwarf star that astronomers have known about is in the backyard. Is the companion of Sirius. This is an optical, on the left hand side is an optical image of Sirius, where you can see the bright Sirius, and there is a companion, it's called the Sirius B. But if you look at X-ray, the Sirius A is not so bright because it's a visible wavelength star. The Sirius B, it's very, very hot, much hotter than the Sirius that we see in the sky. It was first discovered by Bessel, a German astronomer and mathematician, Bessel, in 1844, who noticed that the motion of Sirius, I'm showing this on the bottom left corner, is not very smooth. It has a very sort of an undulating motion in the sky, and he guessed that there is a heavy companion to this star, which is influencing the motion of Sirius with his gravity, with the gravity, and so he could estimate the mass of the companion star. And now we know that this is a white dwarf star, and you know that Subramanian Chandrasekhar had worked on the internal structure of white dwarf stars. So unlike normal stars like the sun, where gravity is balanced by fusion reaction, the pressure coming out of the fusion reaction, these white dwarf stars, the gravity is balanced by what is called the electron degeneracy pressure. And only stars which are less than 1.4 solar mass, mass of the sun, they can balance their gravity in this manner, and that's Chandrasekhar's mass limit. So it's interesting that we have an example right here in our backyard. So this is an artist example of what the sun would look like when it becomes a white dwarf. It will have the size of the Earth, and so it will become very dense and very dim. And so this is a schematic diagram of the evolution of the sun. For example, sun has lived, been shining for about 4.5 billion years now, and after about another 5 billion years, it's going to become a red giant, etc., and become a white dwarf. Now, what about massive stars? Stars which are more massive, they can reach the core temperature is very high, can be very high, and they can keep burning after they have run out of hydrogen. They can burn helium, and then go on to carbon, oxygen, and magnesium and silicon, and go on at this like this, in a sequence like this. And ultimately, their core becomes full of just iron ash, and at this point, it has to stop, because iron is the most stable element in the universe. You cannot have energy by fusing iron into some other element. You have to give energy. So that's where it stops. And as soon as the thermonuclear reaction stops in the center, the star collapses because there's nothing to balance the gravity, right? I mean, this the story of life of a star is basically always balancing gravity, right, with something, the thermonuclear reactions. And as soon as iron is produced, so what happens? The thermonuclear reaction stops, and then there is the whole star collapses. And you can imagine if a long line of, say, people trying to get inside a door, and the door suddenly closes, there's going to be stampede. There's going to be outward pressure. And in the case of stars, this pressure is so huge that it basically shatters the whole star into a huge explosion, which we call the supernova explosion. And this is an example of, it's not in our neighborhood, by the way, but I'll show you some other examples. So this is the famous Crab Nebula. It's a result of a powerful explosion in 1054 AD, which was noted by Chinese astronomers, and they noted that suddenly there was a guest star in the sky. Now, this is an example from our neighborhood. This is a supernova remnant. I mean, the star has been shattered, and there are wisps of cloud in our neighborhood. So this is basically the result of the supernova explosion near Villa. I'll show you the schematic diagram again, going back to the diagram that I shown. On the right hand side, in right hand top side corner, you'll see the Villa. SNR means supernova remnant. So that's where it is. It's pretty close to us. Okay. Now, so there are these supernova remnants. And what happens to the core of the star when the iron core, for example, the iron core, then this keeps collapsing because, again, gravity wins. There's nothing to stop gravity. So it keeps shrinking. And what happens? It becomes a neutron star because the density is now so huge. So a sun-like star, when it becomes a neutron star, it will have a diameter of about, say, 10 kilometers. I mean, the size of a city like Kolkata, for example, right? So you can imagine the huge amount of compression that goes into it. It becomes very dense, so dense that, when electrons and protons would combine to form neutrons, and the whole star becomes just made of neutrons. And this enormous shrinkage also makes the magnetic field very powerful in these stars. Also, it starts spinning very fast, as you know, because of angular momentum conservation. When you compress, it has to start rotating very fast. So what we have is a very highly spinning, very dense star, which may have a large magnetic field. And in some of the stars, you have a magnetic, there's a sort of radiation coming out of these stars called synchrotron radiation. It's mostly seen in radio, but it can also show up in other wavelengths. And if the magnetic field is sort of not aligned, so sometimes you have a situation like this, where, let me see if I can ask, right. So if the magnetic field is not aligned, and the radiation is coming mostly from the magnetic poles, you would have a lighthouse kind of effect. Whenever the magnetic field points towards us, we'll see a radiation, and not when it's not pointing towards us. So we'll see pulses, and so this is the pulsars. So this is how pulsars radiate, and there happens to be a pulsar right in our neighborhood. But it's sort of a very strange kind of pulsar in the sense that most of its radiation comes out in X-rays and gamma rays. So this is a picture that has been taken with gamma ray. It's a gamma ray telescope that has taken this picture. And as you can see the Crab Nebula and this object called Geminga. Now it's towards Gemini constellations, and it's mostly emits gamma rays, so astronomers get given this name Geminga. Now, so this is, I'll show you where Geminga is. So this is the picture I had shown you earlier. This is the local bubble, and the arrow shows where Geminga is. So which basically means that there was a supernova, right? If we can see an object which is a pulsar, it must have been created in a supernova. and of course I have shown the Vela supernova remnant, which is very even closer to the sun. So we can see that there are signs of powerful stellar explosion that has happened in our neighborhood. Geminga is a fossil of that, and other the Vela supernova remnant. And these objects, these explosions, are probably what carved out this cavity and created local bubble. It may not have been just one supernova. I mean, there have been some debate whether Geminga, the supernova explosion that gave rise to Geminga, was responsible for local bubble. But as you can see, this is not really, Geminga is not really at the center. But there have been counter arguments that, well, during the explosion, it may have got a kick, which has taken it away from the center. But there are arguments and counter arguments. But it appears that there have been other stellar explosions even before Geminga, and that's where I would like to talk about in the last few minutes. So this is an interesting piece of rock that was collected from deep sea, from Pacific Ocean. Now, and since then, this is from 2004, and this is from a paper by Knie et al., and this is Physical Review letter in 2004. It's a piece of iron, but it contains a form of iron which is radioactive. So I've written iron 60. So usually iron's atomic number is 56. So it has got 4 more neutrons in its nucleus, and that makes it radioactive. And the most amazing thing about iron 60, this radioactive iron, is that it is very, very rare in nature. It's very difficult to produce this iron 60, and the only place where, only situation where iron 60 can be created is a supernova. All right, so this is very amazing. So we have this piece, and since then, many other places on Earth, people have recovered iron 60. People have now seen under Antarctica, on the Moon. So it looks like, and so the half-life time of this radioactive iron is about 2.5 million years. And you can also date this event. When did this piece of rock fall on the Earth? I mean, definitely it came from outside somewhere. It was not produced on Earth, because it must have been created in some supernova, right? And you can date this from the depth of the layer where you can find this type of iron 60. And people think that this piece of rock, this iron 60, came to Earth, fell on Earth around 3 million years ago. And so it's like, neighborhood, somebody in the neighborhood during Diwali has some firecrackers and something falls on your backyard, right? So an explosion happened nearby, and a piece of a debris fell on the Earth. And you can, one can actually estimate how far away could it have been, this explosion could it have been, so that there's a probability, there's a chance, that good chance that a piece would fall on Earth. And people think that it's about 30 light years and not more than that. Now 3 million years, so this, the supernova then happened within our backyard, within this local bubble. 30 light years is not very far, right? And it happened around 3 million years ago. So, and 3 million years ago, there were Australopithecus, the species, which roamed around in Africa. We know definitely from, for example, the skeleton of Lucy. This has been dated as 3 million years. So when this supernova happened, there were Australopithecus species in Africa. And this is an interesting time also in the evolution of the weather pattern on Earth. Around this time, suddenly the weather pattern changed, and the dense tropical forest in Africa changed into savanna. And as you all know, that change made our ancestors to come down from the trees and become bipedal, and so that weather change has had enormous influence on the evolution of our ancestors. And this is an artist's conception of what a gigantic explosion, which should have been, and which was probably visible even in daylight, because 30 light years away, a powerful explosion goes, and so an object was suddenly visible in the daytime sky and remained visible for some time. And I wonder what Lucy or the others Australopithecus species they thought about when they suddenly saw this. Now, which is interesting to speculate, And now I'll talk about some interesting speculation. So, supernova not only creates a powerful shock waves and can evacuate and push matter away and evacuate a situation, evacuate a region like the local bubble, it can also produce very high energy particles, which we call cosmic rays. And I'm sure cosmic rays are basically, it's not radiation, it's just very high energetic particles. It was first discovered by Victor Hess. I'm showing it on the right hand side on a balloon flight. And he discovered that the high energy particles are constantly bombarding the Earth. And now we know that cosmic rays are mostly produced in supernova explosions. And so that's and on the left, on the bottom, this is a picture of the cosmic ray lab with many detectors in Ooty. If you go to Ooty and go out of the city, this is about 7 kilometers from the town of Ooty, the Tata Institute, and it's run by the Tata Institute of Fundamental Research. And at any rate, what some people have speculated is that cosmic rays from that explosion, which happened 3 million years ago, may have influenced the weather pattern on Earth. But this is sheer speculation right at this moment. There are some ideas that if you have cosmic ray, suddenly the flux of cosmic rays increases. It may nucleate and form clouds and suddenly change the weather pattern. And who knows, maybe what produced this iron 60 and debris fell on Earth. It's like ash from the nearby stellar explosion fell on Earth and may have changed the face of our evolution, maybe even evolution of our species. Who knows? But this is speculation, and it's fun to speculate at some point sometimes. So I would stop here and basically end with this, that our neighborhood is not so boring after all. It may have been witness to very exciting events. So I've talked about the star clusters, young star clusters, and massive stellar winds coming out from them, stellar explosions, many different signs of stellar explosions of objects like Geminga. It's a pulsar, and this local bubble has become a hot topic of research, actually, because of many other aspects. Because such explosions create situations in a galaxy. So when you have cavities like this on the periphery of this cavities, these shock waves, when they push this dense gas in the periphery, it can become another site of star formation, etc., etc. So I'll end here and I'll take any questions if there are. Thank you for the explanation.
Thank you, sir, for such a wonderful lecture and informative talk. Yes, there are certainly many questions. Some of them are written in the chat box.
Okay, so I'll then stop sharing and then come to stop presenting. Okay. So
we can go through one by one. One question was asked earlier by Arundhati Mukhopadhyay. I can ask Arundhati to please unmute yourself and ask your question to sir.
sir. Sir, your presentation was very nice. I
Thank you.
wanted to ask that is there dark matter in the space?
Yes, so dark matter pervades all of these regions. You know, it's there around us, but we just don't know. We haven't detected yet, so we don't know what constitutes dark matter yet, right? So we don't know how to detect it, but it's there from all indications of the dynamics of our galaxy. It looks like dark matter is definitely there.
Okay, thank you, sir.
Thank you.
Okay, the next question I see in the chat box is from, I can see a question, is it possible that a red giant will undergo supernova in future?
No, no. So red giant stars are low mass stars, have core temperatures very, very high, so that it reaches the stage of iron. And red giants are stars which are much lower in mass than. So red giants would not become supernova explosions, no. That is two different branches of stellar evolution. One is for high mass stars, one is for low mass stars.
Okay,
Sir, please explain Chandrasekhar mass in this context.
Okay, so that's a limit on the mass of a white dwarf. And as I mentioned that in white dwarfs, the gravity, gravity is balanced by electron degeneracy pressure. Now, if you want me to explain electron degeneracy pressure, basically electrons are type of particles which so there's a Pauli's exclusion principle. No two electrons can be in the same state, right? So they sort of exclude one another, and that can manifest in a pressure and which can withstand gravity. And Chandrasekhar showed that it is possible for electron degeneracy pressure to hold against gravity as long as the star is not more massive than, say, 1.4 times the mass of the sun. And he worked that out, and that's the Chandrasekhar mass limit. So if you have a star which is more than the Chandrasekhar mass limit, it will not be able to have a stable configuration as a white dwarf. It will keep continuing to shrink and maybe end as a neutron star.
Thank you, sir.
okay.
No, the sun will not be a supernova. The sun will become a red giant, and its core will become a white dwarf star. The sun doesn't have enough mass and the temperature in its core to get to the supernova stage.
But sir, somewhere I have read that Betelgeuse on the Orion will be a supernova in the future. Now it is a red giant, supergiant, something like that. Is it true?
Oh, you see the Betelgeuse. Yeah, well, that's. I have not kept up with that. This was showing some variation in its brightness earlier this year, I think.
Yes.
But people have, I think they found that there's something to do with the stellar atmosphere that is happening. I'm sorry, I don't know the details, but yeah, I mean, it's red giant doesn't become a supernova, but there are supergiants. I mean, red giant, as I said, not all red stars are red giants. So Antares, for example, in Scorpio, that will become a supernova because it's very, very massive. Okay.
Okay.
I'd just like to intervene once, sir. Is that
Yes.
It's all of you, not you, sir. It's to all the others. Let Dipankar go to the chat box, everyone a chance to ask a question. Please don't interrupt him.
Yes.
Let Dipankar do it. Thank you, sir. Dipankar.
Okay. Okay. Thank you, sir. There is another question from Rajdeep Nath. Please, Rajdeep, if you are here, unmute yourself. And the question is, how can you say a particular burning sequence of a massive star?
How can I say?
A particular burning sequence of a massive star.
Well, you mean to say when we look at a star, how do you know that which burning sequence is it in now? Is that
Is Rajdeep here?
Is Rajdeep here?
So we can skip the question if it is not clear.
Well,
Please go to the next question.
Yeah, let me just answer briefly. I'm not a stellar astronomer, but there are detailed evolutionary processes, and people can the signatures of what is happening at the in the evolutionary sequence of a star. So when you look at the spectrum of a star, certain elements will have certain signatures, and so astronomers use those clues to find out at which sequence it is in now.
Okay. The next question is from Mr. Mohit, that if neutron stars are composed entirely of neutrons, then how is the magnetic field produced, as there are no rotating charges?
Yeah, that's a very good question. But again, I'm not an expert in the field of neutron star magnetic field. So, and when I ask my colleagues, so it looks like this is still a topic about which you don't know the details yet. So it looks like the core of neutron stars are so dense that there are it may have signatures of superfluidity, and there are vortices, and also in the crust of neutron stars, it's just not neutron. There are other so charged particles can be there, and so this is somewhat, I'm not an expert in this field, but I think there are people still don't know yet, and this is again a hot topic of research.
Okay, hope you got the answer, Mr. Mohit. The next question is from Mr. Aniket Basu. I think it was answered in this question. Okay, how is iron 60 found in the deep sea?
Yeah. Oh, how? So people just recovered it, and now they have recovered it from, as I mentioned, from Antarctica, from down under the ice. And then you do the chemical analysis, you find that there is iron 60. There's the radioactive form of iron is there.
Okay. There is a question from Debashish Shahu, that gravity curves the space-time. So it is a real phenomenon or just a mathematical tool to calibrate the physical scenarios?
Well, it's as physical, as real as anything else. It's not just a model, because we know that, for example, if the space is bent, then the light path is also bent, and then we know that light actually bends. There are gravitational lenses, for example. We know the examples of. So if you call it reality, I mean, we don't. Yes, it's a model to describe reality, but that's all we can achieve aim to achieve in science, right? We all have only models to describe reality. So if you ask me, is it really so? I don't know how to answer that question. We only have models of reality.
Okay.
It's probably, I'm sorry, it may sound very philosophical or very Kantian, that can we ever know reality? We only have models of reality.
Okay. How can a supernova influence evolution? How can a supernova influence evolution? Evolution of what? This question was by.
Right. Okay, so that was just a speculation. People have been writing papers, especially the Knie et al. They have written papers on whether the cosmic rays from supernova may have influenced the weather pattern on Earth 3 million years ago. And as I mentioned, that change of weather pattern around 3 million years ago was important for the evolution of our the primates. So in that way, there may be connection. It may not be so. I mean, as I say, this is just a speculation, but it's interesting, you know.
Okay, the next question. There are so many questions regarding black holes.
Yeah.
So one question is that what is the lifespan of a black hole roughly?
Lifespan?
Yeah, there is a question
First of all,
from
they're not alive. Oh, if you mean to say because of the Hawking radiation?
Yeah. She has written later that what happens during evaporation of a black hole.
Yeah. Okay. So slowly, because of Hawking radiation, it will lose. I don't know the time scale really. I don't work on that exotic stuff. I work on simple objects. But for yeah, I wouldn't want to answer this question. You can probably look up.
Okay, sir.
I don't have this off the head of my. I can't say.
Yes, there is a question. Yes, sir.
Just I want to remind you that we have a limitation of time, so be careful about it.
Okay, so can we go selective in the questions?
We definitely have to, because it is already 6:15. We have to wind up this session by 6:20 at the most. This session, question answer session.
Okay. Then we can take. Okay. So the question has already been answered. Can a sun go supernova? Okay, so then let's concentrate on those questions related to this session.
Just remember one thing, I have a last question.
Okay. Okay, there is a question from Pronoy Sarkar that if giant star create nebula by supernova, as we know stars born from nebula, so if that star has already enough gas and dust to give birth to another stars, so why that star create supernova?
No, supernova is it's an inevitable result of the stellar explosion. And the star is very, very massive. You see, in its core, when it reaches iron, reaches the stage of iron, the thermonuclear reaction stops. So it has to go supernova. It has to explode. And then, so most of the star, the material in the star is thrown out, and it creates nebula. And that nebula can stay around for another, millions of years until it is again perturbed or shocked by maybe something else, some other disturbance. And then that nebula would form stars, the second generation stars, third generation stars. This is how different generations of stars are produced.
Okay.
I don't know whether I really understood that question.
Okay. Mr. Omlan Kushum Molla has asked that he want to ask a question to you. So please, Mr. Omlan, if you unmute yourself and ask your question. Mr. Omlan Kushum Molla, are you there? Oh, so I think he's not there, so we can skip that question. There are questions related to planets, climate with supernova. I think that has been already answered. There is a question from Devanshu Mukherjee that, sir, what do you think, is there existence of any extraterrestrial element outside Earth? Extraterrestrial element.
Extraterrestrial element.
May I ask a question?
Yes.
May I ask one question?
So I'm not sure what do you mean by extraterrestrial. I mean, are there elements that are not found on Earth but are found elsewhere? Yeah, for example, iron-60 is not really found. It's very, very rare. And so if you find such elements, then you have to conclude that it has come from somewhere else. And
Hello, sir.
yes.
Hello.
Yeah,
Sir, I am
Mr.
Omlan. Yes, sir, I am Omlan. I missed a chance earlier because my mic wasn't working. So, sir, what I want to ask is that you mentioned about molecular clouds. Okay. So the density of molecular clouds is very less. You mentioned it is as a 10⁻³ atoms.
No. Molecular clouds are dense. So the 10⁻³ particles per cc was for local cloud, a local bubble.
Okay. So are these molecular clouds? So these molecular clouds should be affected by the gravity of the stars and the celestial objects that are there. So
yes.
So do we observe the density of these molecular clouds? Do we observe that they are more dense towards the stars? Means the presence of molecular clouds, which are at a distance of less distance from the stars, are those clouds more dense than what is spread throughout the whole space?
Yes. So molecular clouds are very dense. That's about 10⁵, 10⁶ particles per cc per cubic centimeter. And are you asking the question how we know, or so we know that this is very dense?
Yeah. So these molecular clouds will also convert themselves. Means as the density increases, these also convert themselves into those particles do they get inculcated into the stars and increase the size of the stars.
So, see, the giant molecular clouds are it's a stable configuration because the gravity is balanced by there's turbulence going on, and there's also their own gas pressure. But in certain regions of the molecular clouds, you can create a disturbance. You can compress this, and then if you suddenly increase the density of that region of the giant molecular cloud could be very, very large, but in a small region of that cloud, if you push and increase the density, then you can create instability, and that's called the Jeans instability. And then it will keep collapsing, and it will form into fragment into clouds, and then basically it will form stars, and that comes out of what's called the Jeans instability. Basically, for that you need certain density and threshold density and certain size. The cloud has to be of certain size so that it can start collapsing.
Okay, Shoykot sir, your question, and then we can finally go to Vasudev sir.
And no one else? Are we cutting it off now?
Your question, and then
Dr.
after,
Nath, can we continue for another just 5 minutes? There are a lot of people.
Yes. Sure.
Divankar, please carry on for another 5 minutes.
Okay. So let me check. Okay, there is a question from Tomal Mukhopadhyay. Is there any other hypothesis about the origin of the gas bubble around the sun and its neighborhood?
Any other hypothesis means, well, I mean, it's clear that must have been supernova explosions which created this cavity. Now, we don't know when and where this sequence of supernova, or was it a particular set of supernova that created this? We don't know yet. And and there is research going on, and people are working on the history of a local bubble. But it's clear that, you know, you have to have supernova. Now, how many supernovas did it take to create this? We don't know yet. And when did they happen? We don't know yet.
There is a question from Srija Sarkar that how does a supernova completely destroy a star?
Well, that explosion is because the gravities of the massive star is so huge, so powerful, it starts collapsing on its own, and then suddenly it finds that, you know, the core is it's become iron ash, and that is a huge powerful explosion, and that powerful explosion can be in the process, and the
I think we are having some network problems.
Network problems, yes, sir.
Just wait for a couple of seconds.
Yeah, surely.
Can you hear us, sir? If not, sir, can you hear us? Oh, there's a problem with Dr. Nath's connection.
Sorry.
Yes.
I got thrown out.
Welcome.
Something happened.
Welcome back.
Oh.
And so what I was saying is that during the process of the formation of the neutron star, particles called neutrinos are emitted, and these neutrinos can push and you know, finish the job of destroying the whole star. So the neutrinos are also very important.
Okay. There are so many questions coming in, sir. Can we continue?
Can we do one thing?
Yes, please.
Since we have your mail address, questions, compile it together and send it to you. So once we get back the answers, we can mail them back, the ones who have asked the questions.
Yes. So you have my email address. You can.
Yeah.
Right.
Yeah, we can do that because there are so many questions in the chat box, and there is also some few questions in the YouTube live streaming also. So there are still a few
For
questions.
all of the viewers and all of us here, we decide on this thing that we will compile all the questions and send it to Dr. Nath. He will reply as according to his convenience.
As much as I can. And as much as I can.
Yeah.
I mean, I don't claim to know everything. Okay, so I work on a very, you know, focused field in astrophysics. So, you know, and it is a very vast field, from stars to galaxies to all kinds of phenomena. So as much as I can, I will try.
And once we get those feedback from Dr. Nath, we'll send it to you individually. No problem with that. Now the one question I'd like to ask, sir.
Yeah.
Yes.
Is nothing related to your lecture. It is simply that I just want to tell you something.
Yes.
Since till today, we were looking up at the sky, hunting for nebulas, photographing them, looking at those regions of the sky a repeated number of times, without knowing that so much was going on up there. So much had taken place in those regions. The regions which we have seen so many times. We had looked at the summer triangle, we had looked at the winter triangle, we had shown school children, college goers, they look, this is that, you find this there, you find that, but never we did know that these things were happening up there and these had already happened there. And this was the reason what we are looking at there. Frank, sir, that region or those regions of the sky will never be the same again once we get our hand on the telescopes. It will never be the same again. Now the $1 million question.
Yes.
The question, I believe, will be on behalf of all the viewers today. The question is, sir, when are we going to have you back again?
Oh, well,
Can we work on that?
yes, sure. Yeah.
Thank you very much. Thank you very much, sir.
It was very nice. Thank you very much, and for having me here, and for interacting with people through your platform.
So now we have a formality. Mr. Basudev Bhattacharya, the president of the association, will. Sir, Basudev, sir.
Sir, also have a question for Biman.
Sir, I had a question.
Oh, my question.
Yes, sir.
Can you hear me?
Yes.
Actually, my question was that if nothing heavier than iron can form in the nucleus in thermonuclear process,
Yes.
then how could the iron, nickel, cobalt, I'm
A
sorry,
very nice question. I'm glad that you asked
gold,
it.
platinum,
I was going to, yes, right. Absolutely. Right. So as I mentioned that, you cannot get energy out of fusing iron into heavier elements. So you need energy to produce elements heavier than iron. And that energy is supplied during and by the supernova explosion. So during the supernova explosion, that powerful energy, the energy that is supplied by the supernova explosion, that creates all the elements that you just mentioned, nickel, cobalt, all the way up to uranium. So you need supernova, for the lead that we have on the Earth, for example, and all the other, trans-iron elements.
Thank you.
Thank you.
Thank you. Now, on behalf of Skywatchers Association, and on my behalf as the president of the association, I thank Professor Biman Nath for the nice lecture they have delivered to us.
Thank you very much for having me here.
Now, one thing, very revered our I forgot the name. Anyway, there is a speech by the Dalai Lama once said that when you speak, you only repeat what you already know, or you think you know. But if you listen, you may learn something new. And we are in quest of knowledge, all people. And a mission to propagate them or to share that knowledge to with the very low, down the level commentator. And we acquire knowledge from various sources like you and other places. We seek for others. In Rabindranath language, সাহিত্যের আনন্দের ভোজে নিজে যা পারি না দিতে নিত্য আমি থাকি তারই খোঁজে. So we always look for somebody to enrich our knowledge. So thank you very much for that on behalf of that. Thank all the participants because you are also in quest of knowledge. You are present here. I thank all our members, Dr. Dipankar and others, and Shrikant, to organize this thing. Without them, it could not be possible to get together like this or have this webinar. And everybody, and for present, and so wish to get you again and meet all of us again with a new webinar. And thank you all.
Thank you.
As is customary with Skywatchers Association, let's end this round with a big applause for Dr. Nath.
Thank you. Thank you. Thank you.
Thank you, sir. Thank you very much.
Thank you very much.
Thank you. Thank you.
Thank you, sir.
So the participants can let the meeting know.